So big day, big idea, and today's the day we're going to introduce the idea of rotating magnetic field and its need and how we're going to do that. But let's first review the basics we have learned. First of all, a rotating loop in a stationary magnetic field gets an EMF induced in itself, and second of all, a current loop in a stationary magnetic field feels a torque. The torque is given by the equation K, some constant BR cross BS, and the interpretation of the dot product and interpretation of the cross product is that the rotor magnetic field always tries to align itself with the stator magnetic field. That is the interpretation. And some basic about magnetic field is that if you have a current wire, simple current wire, then the magnetic field due to this current wire can be found out using your right hand rule. You put your thumb in the direction of current, and the fingers you curl will give you the direction of the magnetic field. That's what I have showed in here. And if you use this rule in continuum, you will find out how and what the direction of the magnetic field will be for a loop, right? We have given 4 points here, and if you use your right hand rule in all these 4 points, in all these points continuumly, you will see that the magnetic field tries to come out of the path. That's what I have denoted. So what's the rule? What's the rule for the loop? For a loop, the overall rule is that you put your you curl your hand in the direction of the current flow, and your thumb will point into the direction of the magnetic field, right? And that's all the basics we need to review. All right, so we are going to come to the big picture right now, the rotating magnetic field. We have seen in past lecture that tau induced is going to be dependent on the cross product of rotor magnetic field and stator magnetic field, and rotor magnetic field always wants to align itself with the stator magnetic field. So the basic idea is, what if we could rotate the stator magnetic field? If we could rotate the stator magnetic field, then the rotor magnetic field would always try to align itself, but it would always fail, so it will keep on rotating always. And that's what we want, that's what motor does, right? So how are you going to produce a rotating magnetic field in the stator? First of all, the last lecture scenario where two bar magnet was there is impractical. We're going to produce magnetic field by currents right now. Okay, so what sort of currents we're going to use? We're going to use three-phase currents. Three-phase currents means the currents are going to be 120 degree apart from each other. And how are you going to use the current? We will have a circular hoop in the rotor, or a very simple circular hoop, and we will have the setup is that we will have 6 holes for windings, and the winding holes will be 60 degree apart from each other. And we will put our wire we will place our wire into the windings, right? So the second rule is that the same phase current windings will be 180 degree apart, right? You see, in this winding comes out, then goes in, and then goes into the pace. So you see, these two are same phase windings because they have same phase currents. These two are same phase windings because they have same phase currents, and these two too, and they are 180 degree apart. And the third rule is that like polarities of different phase current windings will be 120 degree apart. You see, for this phase the current is coming out of the phase here. For this phase is coming out of the phase in this winding and here, and you see they are 120 degree displaced from each other. So like polarities means all those windings where the current is coming out or either coming in to the phase, like these three are also 120 degree apart, and this sort of a special setup is what we call a three-phase setup of windings, right? And we are gonna use this three-phase setup of windings to produce a rotating magnetic field, and we're gonna see now how is a rotating magnetic field produced. So this was the setup. Same phase windings are 180 degree apart, and different phase but same polarity windings are 120 degree apart. That's the setup. And so we have to use our right hand right now to find out the direction of the magnetic field. Okay, So if we use our right hand for this face, that means a dash a face, and we're going to see that it's coming out of the face and then going in. So the loop is kind of, current is going like this. So if we curl our hand, then our thumb is going to point in this direction. So magnetic field produced will be like this. All right. And then we see for this face the current is coming out and then going into. So if we use our hand, the magnetic field is going to be like this, and for this face again the magnetic field is going to be like this if we use our right hand rule betterly. All right. Now we are going to use some rules to find out what will be the magnetic field value. We know B is equals to mu I, so if we apply that, B is going to be mu over G, some parameters, times I, right? So magnetic field produced due to these windings A to A dash is going to be mu over G, and the current that's going in these windings, and that will be simply Im sine omega t. And B dash is going to be mu over G Im sine omega t minus 120 degree, and BCC dash is going to be mu over G Im sine omega t minus 240 degree. All right, and that's the three magnetic fields we have found out. So we have to add them finally, right? But before we'll make some simplification. We'll call this thing mu over G times Im, simply Bm, the maximum of a magnetic field, Bm. All right. And the problem with adding them is that we have to consider them as vector, and they are not aligned in the same direction, so we'll add them vectorially. Magnetic field is a vector, right? So we need a coordinate first of all. So we're gonna put some coordinates and reference coordinates right now. We're gonna call this direction as x, positive x, and we're gonna call this direction as positive y. So we know this will be 120 degree, and all the angles will be 120 degree because our winding is 120 degree. And in the same way, if if we curl our hand, the resulting thumb will also be 120 degree apart from each other. So with respect to our reference coordinate, BA dash is going to be Bm sine omega t, but fully on the x-y direction. So I will put a unit vector of x in here, and then B dash is going to be Bm sine omega t minus 120 degree. And now what will be the unit vector on this direction? The unit vector is going to be cosine 120 degree x hat plus sine 120 degree y hat. We have decomposed it basically. Okay. And what will be BCC dash? It will be Bm sine omega t minus 240 degree. Now what will be the angle from x coordinate? The angle difference is 240 degrees, so it will be cosine 240 degree x hat plus sine 240 degree x hat. So basically it means Bm sine omega t minus 120 degree minus half of x roof plus half of y roof, and it means Bm Bm sine omega t minus 240 degree, and this is going to be simply root 3. This is going to be simply what will be the value of cosine 240? Root 3 by 2 x roof plus minus root 3 by 2 y roof, right? And if we put the values on, now we can add them simply on the x hat direction and on the y hat direction. So if we try to find out b net, and you're gonna take the x roof components first of all, we have to add these three, and we will take the x hat components first, and then we are going to take the y roof components, y components later. Alright, so what's the x roof component here? The component is bm sine omega t. What's the x roof component in here? It is going to be minus half bm sine omega t minus 120 degree. And what's the x roof component in this portion? It's going to be root 3 by 2 bm sine omega t minus 240 degree. Okay, the y roof component, BAA dash has no y roof component, BB dash has y roof component of half bm sine omega t minus 120 degree, and then minus root 3 by 2 component from BCC dash is going to be sine omega t minus 240 degree. Alright, and now we'll have to add them. Okay, there was a bit error in the calculation. It was supposed to be root 3 by 2 instead of half, and it was supposed to be minus half instead of root 3 by 2, and I have made those error corrects, and finally we get these equations. Okay, now we have to add these different sinusoids with different amplitude and phase angle. So how can we add them? I'm gonna show one addition for demo purpose, and we can add them by trigonometric identities, or we can add them by phasors, but nothing can be better but easier than adding by complexifying it. Alright, so if we complexify it, it is going to be root 3 by 2 bm. This sign is simply imaginary part of e to the power j omega t minus 120 degree, and we have taken root 3 by 2 bm common, and this sign is going to be the imaginary part of e to the power j omega t minus 240 degree. So inside this imaginary portion we are going to apply complex algebra. Okay, if we take e to the power j omega t common, then we get e to the power minus 120 degree minus e to the power minus 240 degree. Alright, and it turns out that if we evaluate it, we are gonna get e to the power minus j. Obviously, if we evaluate it using cosines and sines by Euler, we are gonna get root 3 e to the power minus j19. Just put it in the calculator and you will see the result, and is going to be em e to the power j omega t minus 90 degree and root 3 overall. And now we can simply take the imaginary part of this exponential, and is going to be root 3 becomes 3 by 2, and bm sine of omega t minus 90 degree. Okay, that's the y component addition we have done by complexifying. And if we complexify x coordinate addition, then we're going to find out that it will be equal to, sorry, there will be a minus on here. Yeah, yes, there will be a minus which I've taken out. No, this is positive only, and if we convert this sine to cosine, this is going to be negative 10, and it will turn out to be minus 1 by 5 bm cosine of omega t. Alright, and remember we have a cosine on here and sine here, so if we go in 90 degree away, we come out from sine to cosine. If we go 90 degree away, we come out to negative of cosine. That's what we have used. And in the same way, if we try to find out the x component of the net magnetic field, is going to be 1 by 5 bm sine of omega t. So what will be the ultimate total magnetic field equation? This is going to be simply equals to 1.5 bm sine of omega t x hat minus 1.5 bm cosine of omega t y roof. Alright, and from this equation you can see both the x component of the magnetic field and the y component of the magnetic field, both are sinusoidal functions of time. So that means it's going to change sinusoidally, and if you add them, square them and add them up, you're going to get 1, which is a property of circle. And so it is going to rotate rotate. It's going to rotate in space for some, let's say, some time of moment when omega t is equals to 0. We're gonna get b is equals to 1 by 5. This is going to be 0 and minus 1 by 5 bm y hat. So it's going to be totally oriented into y hat direction, and let's say in some moment when omega t is equals to 90 degree, that means time has increased, the net magnetic field is going to be only for the sine component, so it's going to be 1 by 5 x roof. So it's going to be like this. Sorry, this was negative direction. Yeah, so as time passed away, we came from negative y hat direction to the positive x coordinate. That means we have made a counterclockwise movement, so we can say the rotation is counterclockwise. So that's the idea for a rotating magnetic field, and that's what we do to get rotating magnetic field. Three-phase current setup, you complexify, add the component vectorially magnetic field components, and you get a rotating counterclockwise rotating magnetic field. All right.